Why don't comets lose their tails? Round 2. Where are all the Milky Way pictures from space? And what if you jabbed a black hole with a stick? All this and more in this week's question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I will gather them up and I will answer them here. All right, let's get into the questions. Thomas Shields. I don't think you answered Scott's question about the comet. He wasn't asking why did the tails and trails last for tens of thousands of years. He was asking why the comets themselves don't lose enough matter during their regular approaches to the sun or disappear sooner. So after a question show that we did, I guess last week, but I'm not sure exactly how many shows ago it was, but why don't comets run out of tail fuel, I think was the thumbnail that we had. And a lot of people in the comments said, you answered the wrong question. You answered, why do the tails last a long time in the solar system, but not like, how can the comets be continuously producing tails for long periods of time? And I apologize that I answered the question I wanted to answer as opposed to the one necessarily that was being asked. And so here's the other version of that answer. So yeah, so comets, right? They come from icy regions of the solar system, and they are balls of a mixture of rock and water ice, as well as other volatile elements. And when comets get relatively close to the sun, within the orbit of Saturn, Jupiter, they start to produce this tail that the solar wind that is striking the comet starts to cause the volatiles on their surface to boil off and create this tail that is following behind them in space. Now, the comet tail points away from the sun. And so that's why when a comet is moving towards the sun, it looks, it's got this tail going behind it and makes sense. But then when the comet is moving away from the sun, the tail is still moving away from the sun. It looks like the comet is following its own tail. But absolutely, this material is being degraded by the solar wind. And there's a limited amount of material that's on the surface of the comet. And it lasts somewhere on the order of thousands of years. And it really just depends on the orbit of the comet. And so in some cases, let's say you've got a comet like Halley's Comet that gets in relatively close to the sun, but then goes pretty far out into the solar system. Astronomers have been tracking Halley's Comet because it's a very bright comet. It's very recognizable for about 2,000 years, and it still produces a tail every time that it comes by the sun. But there are other examples of comets that maintain within the orbit of, say, Jupiter. They don't get that far away from the sun. And it appears that within just a few dozen orbits, they've lost their tails. They no longer have these volatile elements on the surface of the comet. Now, something that's really interesting is that over the last couple of decades, astronomers have found objects which are asteroids, and yet they seem to produce a comet-like tail, or a fairly diminished tail, but still. And so what's probably happening is that you're getting this loss of material on the surface of the comet, the stuff that the solar wind can easily reach. But then once that's all gone, you still got lots and lots of material that is underneath the surface, but now it's all just covered in this shell of rock. And so if something happens, like the comet gets hit by an asteroid or breaks apart in some way, then all of this material is then freshly revealed to the solar wind, and then it can generate a tail again. So comets definitely don't last forever. They last a few thousand years, depending on their orbit, how close they get to the sun, and how far away they are from the sun at the farthest point of their orbit. If there's like a third version of this question, I'm ready. JDMM4UB. How come there are so few pictures from the Milky Way taken from the space station? I think they'd have a much better view than we do on Earth. The astronauts on board the International Space Station absolutely have a better view of the Milky Way than what we have down here on the surface of the Earth. They are above the atmosphere, and so they get this clear view. Their eyeballs have become space telescopes, and they're able to look out into the cosmos. And I've had a chance to interview astronauts directly about this question, especially the ones who are amateur astronomers. I talked to Ron Guerin and Don Pettit. And Don Pettit actually is on the International Space Station right now, although, we were having a beer at a conference and not, talking to him on the station. And what the impression I get from them as amateur astronomers, like they own telescopes, they go out, they do photography of the night sky, that the experience of being on the International Space Station is like you're being in the darkest skies you've ever been in on Earth, and then some. And that in fact, it's actually a little disorientating because just the regular stars are all so bright that it's really hard to orient yourself, to recognize the constellations, because just more and more stars are out there. And you know, if you've ever been in really dark skies, you've experienced a version of this where there's so many stars and they're all so bright that you actually can't find the obvious constellations that you're very familiar with. But the Milky Way apparently does look amazing. And so, like, why are we not seeing a lot of images of the Milky Way taken from the space station? So there's a couple of reasons. One is that the space station orbits around the Earth every 90 minutes. And so it's in the sunlight, and then it's in the shade of the Earth, and it's in the sunlight, it's in the shade. And so if you have cameras sitting outside that are attempting to do astrophotography, they're going to, for a time, be in complete sunlight, and they don't like that. And so you're going to need to switch the cameras on, switch the cameras off, and so on. Also, a lot of the cameras, like the automated cameras that are on board the International Space Station, are pointing down. They're looking at the Earth. You know, in some cases, they do actually get like a nice view off to the horizon, and you can see the curvature of the Earth, and then you can see the sunrise over the horizon and things like that. Now, there were a bunch of automated cameras installed on the space station, and there are still some, which take pictures in different angles on a regular rate. And a lot of people made really cool time-lapse videos of the Earth passing under the space station. You could see auroras forming, and then it was in day, and then it would go into night, and you could actually see the Milky Way rising above the limb of the Earth. And then the other thing is that when you do have an astronomy-minded astronaut on board the station, they've got a bunch of cameras at their disposal. And Don Pettit is up there right now, and you know, has talked quite a bit about how he takes pictures from the cupola, which is this cool observing room on the space station. And he has taken just amazing pictures of the Milky Way seen from the space station when it's in one of these shaded periods. And so hopefully, you know, Chad's been putting up a whole bunch of really cool images of the Milky Way seen from the space station. So it's just like most of the time it's looking down at the Earth during the day, or there's images of the astronauts inside the space station. It just has to be like an astronaut has to decide that they're going to go look through the cupola, point their camera, take images of the Milky Way or the moon or other things that are going on. But there are tons of those pictures and even time-lapse videos of it. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Antoine, David Lutenberger, Miguel, Andrew Blakers, Maxime Abran, and Blake. Join the club at patreon.com/universetoday. IARC-SIM. In 5 billion years, the sun will go through a giant phase and expand around the Earth and the moon. Won't the Earth and the moon get dragged so close to the sun by friction with the sun's gases that they won't meaningfully exist in 50 billion years? So that 50 billion years number was from a previous show where I said what the time it would take for the Earth and the moon to tidally lock to each other, to become a true double locked planet. And so a good example of this is Pluto and Charon. So in the case of Pluto and Charon, Pluto is locked to Charon and Charon is locked to Pluto. They are both gazing at each other as they orbit around a common center of gravity between the two of them. And with the Earth and the moon has locked to the Earth, but the Earth has not locked to the moon. And so because of the way the tidal forces work and the conservation of orbital momentum, the Earth's rotation speed is slowing down and the moon is moving farther away. And eventually the Earth will lock to the moon, but it'll take about 50 billion years. And I think I even said in the question that, it doesn't matter because the sun will be dead by then. And so, yeah, around 5 to 7 billion years from now, the sun will bloat up as a red giant as it uses up all of the hydrogen fuel in its core to become this red giant. It will consume Mercury. It'll consume Venus. But astronomers aren't entirely sure that it's going to actually consume Earth and the moon. And this just goes back and forth. 1 week we'll report on Universe Today that someone's produced a paper that says that the sun is going to consume the Earth, and then someone will produce a different paper that says that the sun won't consume the Earth, and we don't really know. And the question comes from the mass loss. So as a star like the sun, a main sequence star, gets into that red giant phase, it starts to, it bloats up, and then it puffs out these outer layers and then shrinks back down and loses some of its mass. And then it does it again and then keeps going back and forth. And each time it sort of throws this shell of material out into space. And eventually it ends up losing whatever mass that it does. And so the mass loss will cause the Earth and the moon to change in their orbital position. And it might very well be that, that the Earth will orbit a little more closely to the sun will bloat out, and it will actually get captured by that red giant phase. Or maybe it won't. And so, this is one of those continuing unfolding mysteries. And maybe we're just going to have to wait 7 billion years to find out what happens. But whatever the case, the solar system will be unrecognizable in 50 billion years from that final day when the Earth has finally tidally locked to the moon, or both were long gone, gobbled up by the sun. Kyle Stedward had a random thought. If you could orbit right on the edge of an event horizon and then have a long pole and put the pole through the event horizon, what would happen? So the question you're asking is that if you were orbiting around a black hole and you're right at the edge of the event horizon, this place where the escape velocity of the black hole exceeds the speed of light, and then you took a pole and you put the pole down into the event horizon, what would happen? So, obviously the first thing is what is the tensile strength of the pole that you are using? Because it needs to overcome just immense tidal gravitational forces that are going to tear it apart at an atomic level. And no matter what the pole is made of, it is going to be just pulled apart, and, you're not going to be able to bring anything back up. But I'm assuming that you have created this pole out of some sort of unobtainium, something that is so strong that it can never be. Maybe it's made of black hole. Maybe it's made of neutron star, or even tougher than that. It cannot be shredded by a black hole's tidal forces. And so you kind of then have to go back to the first rule of the event horizon, that nothing, not even light, can escape its grasp. And so there is no amount of force that you could put onto that pole to try and pull it back up that would allow it to escape the pull of the black hole. Once you're inside the event horizon, all paths lead to the singularity, including the pole. Now, obviously it's going to pull you in with it. So, but there's something, you can't break the rule, which is you can't get out of it. Even if you, and because the pole strong enough to handle the tidal forces is impossible, that alone will make the problem not work. So even if you could, you can't get it out. It will be held fast. Graham Goins. When did the universe become our universe in a greater universe? Well, we don't really know what caused the universe, but essentially by the best measurements that astronomers have been able to make, the observable universe that we find ourselves in today has been around for 13.8 billion years. And so right now, we can look to the left of us, 46 billion light years away. We look to the right of us, 46 billion light years away. And yet in the past, those regions were 20 billion light years apart. And then at one point they were just a few 100,000 kilometers apart. And then there was a time when the entire observable universe, everything we could see, was the size of a volleyball and maybe smaller. Maybe the size of a pea, we don't know. Or maybe like a singularity, infinitely small. But that was just one component of the larger universe. And so, if you had this volleyball-sized version of the universe, then right beside of it, there was another one and so on. And so the question that you're getting at is like what came before, right? Like what was the environment of the universe that then we got our local version of space starting to become less dense over time and become the universe that we see today. And, obviously you can think, well, okay, there was another version of our universe right beside us, and they're going through the same thing that we are. And then there's the people that kind of split the difference, right? The people who are in between us and the universe beside us, and they've got their own sphere, and they're seeing a little bit of our universe and a little bit of the next universe. And so it's thought that if the universe is infinite today, then it was infinite before this de-densification started to happen. But like, what set this off in the first place? And, we don't really know. In fact, we don't know at all. And anyone who tells you doesn't know. They're guessing, or, someone told them, or, they've got a theory, but they don't have any observational evidence to back it up. But probably the strongest theory that's going right now is this idea of inflation, that there are problems with the Big Bang in the flatness of the universe, the lack of magnetic monopoles, the way that parts of the universe shouldn't have been able to sort of average out their temperature, and yet they did. And so this idea of inflation, that before we got just the regular de-densification of the universe, there was this period that was sort of incredibly short, like a fraction of a second, where the universe went through this doubling in size. And sort of one of the interesting things about, the underlying requirements for this idea of inflation is that it was going across a larger volume of space, and that different parts of this universe were inflating at different times and different speeds. And it could very well be that there are parts of the universe that are still inflating today, billions of years later, and other places where inflation stopped before we did. And that in each one of these local areas of the universe, they potentially have their own underlying laws of physics. And you can imagine, each one is gone off and inflating in its own place and pushing the other universe parts away from them. And we could never reach one of these alternative universes. So one possibility is that just the entire universe is just getting less dense over time. One possibility is that there's sort of this larger landscape of universes within the universe, and they're sort of experiencing different versions of themselves, and they're not going to overlap. So, we don't know. We don't know is the answer. And that's got to be fine. Like you've got to be okay with the possibility that we may never know the answer to this question. 1 million years into the future, our descendants will go, where did the universe come from? And the astronomers will go, I don't know. We've looked for 1 million years for any shred of evidence that connects this universe to what came before, and we haven't been able to find anything. And so everything is still on the table. We still don't know. And hopefully in 1 billion years, the astronomers then will have a better answer. Thanks everybody who asked your questions in the YouTube comments, and everybody who joined me for the live chat. This was the first episode that we did in European time, and so it was an entirely new group of people that were in the chat for the live show. But still, we had almost the same number of people for the regular Monday show that I do at the normal time. And so it was a huge success. We're definitely going to do this again. Next up comes the Australian Asian time zone. Now, I'm going to talk a little bit about my current video game obsession, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Barry Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Spiderswap.io, and Stephen Filer Munley, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So, like many people out there, I've been playing Path of Exile 2, and you might not know that I'm a Path of Exile player, but I sure am. I've been playing for about 5 or 6 years. I'm at the point now where I mostly play solo self-found. I like to make my own builds. I like to try to get as far as I can into the content. On the last league, I was able to, on my own build, able to get all my void stones. For those of you who have no idea what Path of Exile is, that's fine. But for those of you who know, that's good. But I'm playing Path of Exile 2, and so far my initial feeling has been, it's fantastic. I love it. It's exactly what I wanted. Now, I know a lot of people think it's too hard. A lot of people think there's not enough loot. I think it's great. I enjoy the suffering and the sacrifice. and learning and experiencing a brand new game that I've just have never tried before, and sort of making my own way as I go. And it's exactly the kind of experience that I really enjoy. So, and I'm playing it all on the Steam Deck. I'm not playing it on a computer, just entirely on the Steam Deck, which is great because then I can hang it with my wife, parallel play while she's watching TV. So if you are on the fence and you're wondering if it's a good game, it's got my seal of approval, and they're not paying me to tell you that. All right. Hopefully I will have some spare time to see you next week.